This video is on Coulomb's law. Coulomb's law is an equation, and it helps you find what is the electric force in newtons between two charges that are a certain distance apart. The Q's represent charge magnitudes, and the unit, as I've written here, is capital C, which is coulombs. K is a constant equal to 9 times 10 to the ninth, and then it has some rather intricate units there, but those are required in order that the force comes out in newtons. And then R is the distance between the charges. You might remember for the rest of your life that there is a rat in the word separate. It's very easy to spell the word separate with an E there and an E right there. And that's wrong. There's a rat in the word separate. So if nothing else from this video, you'll learn that the proper spelling for separate is with two A's and only one E there at the beginning. All right, so what we're going to do here is we're going to see if we can solve this problem. We're going to determine the net force on Q1 due to the other three charges. Q1 is up here in the upper left. All of these charges exert forces on each other. But what we're going to need to do is we're going to need to use Coulomb's law first for those two charges, and then let's say for these two charges, and finally for these two charges. And those three forces then are going to have to be added in the vector sense to give the net force on Q1. Let's show you what we mean by that. So the force on charge 1 is equal to, Coulomb's law is K sub C, which is 9 times 10 to the ninth. I'm going to leave the units off here because the units are all going to be right. The charge of Q1 is 4 microcoulombs. That's 4 times 10 to the negative 6th coulombs. And the charge on 2 is, the magnitude of the charge is 9 times 10 to the negative 6th coulombs. I'm leaving the sign off of these charges when I do this Coulomb's law equation, and we will just think what the direction of the force is here at the end. Then we need to divide by the distance between these two. You can see over here on the right that that vertical distance is 3 centimeters or 0.03 meters. And if you crunch that out using your exponent key on your calculator, you get this value, 360 newtons. And now, what is the direction of this force on Q1? These two are attracted to each other. So Q1 is going to be pulled down. What about in Q2? We don't care. Due to Q1, it is also 360 newtons, but it is up. But that isn't the question here. The question is, what's the force on Q1? So it's the down version that we want. Then we're going to do this sort of situation twice more. Once between, as I showed a minute ago, charges 1 and 3, and then finally between 1 and 4. So let's go through that. I'll show you the work rather quickly. You can verify this on your calculator in your own time if you wish. So the force on charge 1 due to charge 3 is Coulomb's constant, 9 times 10 to the ninth. The magnitude of charge Q1, 4 times 10 to the negative 6th. Now, what's the magnitude of charge 3? It's 2 microcoulombs, 2 times 10 to the negative 6th. And what's the separation between those? Well, this is a hypotenuse of a 3, 4, 5 right triangle. So the distance between those is 0.05, and remember to square that denominator. When you get that answer, that comes out to be 28.8 newtons. And what's the direction of that force? Well, again, we're focusing on charges 1 and 3. We can see they're both positive. So this is going to be a repulsive force, and it's going to act, therefore, in that direction on Q1. Now, what we're going to need to do is we're going to need to break that into its components. I trust that you learned how to do that in a first-year physics class, and you're welcome to check if you wish. 28.8 newtons in that direction, given the dimensions of this figure, ends up being about 23 newtons in that direction and 17 newtons in the positive y direction. I'm not going to take the time to show you how I got those components. I trust that you know how to do that, or you can figure that out at some point. Let's do this one more time between charges 1 and 4. 9 times 10 to the 9th. Magnitude of charge Q1, 4 times 10 to the negative 6th. Magnitude of charge 4 is, again, we're leaving the negative sign off because we'll just figure out in our heads by thinking which way the force is going to act. K, Q1, Q2 over R squared, and the distance between charges 1 and 4 is 4 centimeters, which is 0.04 meters. Again, I'm leaving the units off to save time, and also because I checked them and I know that they're right. But whenever we write an answer, we never, ever, ever leave a unit off an answer. Whenever you hit equals on your calculator, you better write the unit that has. All right, charges 1 and 4, we can see that this is an attractive force, so it's going to pull charge 1 to the right. What we do now is we need to add that vector in the downward direction, this vector in the upward direction. Let me put a rectangle around the x direction components. There we go. So these ones that I've put an oval around give us a net. Let me scoot this up just a bit so you can see this. The force in the y direction is 360 down and 17 up. That's 343 newtons in the downward direction. In the x direction, that comes out to be 157 newtons in the positive direction. And then when you use the Pythagorean theorem on those to determine the magnitude of that overall force, I got 377 newtons. And again, I'm not going to show you how to do this. Hopefully you learned it in a previous physics class. If you use your inverse tangent key correctly, 65 degrees below the positive x-axis. We're not worried about significant figures here. We're just making sure that we've gone through one procedure so you can kind of see how this is done.